Okay, we are at the last section, section 22.6, um, motion of a charged particle in a uniform electric field. Let's go to the PowerPoint. This is going to be a single slide, but I am going to do a problem to help, hopefully help understand how we use this information. So here we see a E field set up by two parallel plates separated by a distance d. Um, the positively charged plate is on the left, the negatively charged plate is on the right, and you have a charged particle, a positively charged particle next to the right next to the plate. So since the plate is positive and the particle is positive, there's going to be a repulsion. You can see the force vector there. The positive plate is going to repel the positive particle, so it's going to move to the left. At the same time, the negative plate is going to attract that positive particle. The opposite signs attract, positive signs repel. So there's going to be um, a force from the positive plate and a force from the negative plate, and the sum of the forces is equal to QE. E is the electric field formed by these two plates, but also we know from Newton's second law that the force is equal to the mass times the acceleration. So if we solve for the acceleration, we see that the acceleration is force divided by mass, with the force is QE over m. And that actually ends our discussion. I'm going to go on and do a problem to show how to use this information. So we bring up the iPad. Um, there we go. And I don't know that. Let's go. All right. Let me read the problem statement. A proton accelerates from rest in a uniform electric field of 640 newtons per coulomb. At one later moment, its speed is 120 megameters per second. That's non-relativistic because v is much less than the speed of light. The speed of light being 3 times 10 to the 8 meters per second. We find the acceleration of the proton. For A is find the acceleration of the proton. B is over what time interval does the proton reach this speed? C, how far does it move from this time in this time interval? And D, what is the kinetic energy at the end of this interval? Okay, let's look at what we know. And I've got some highlighted areas here. A proton accelerates from rest. That means the V initial is 0. If it's started from rest, V initial is 0. V final is 1.2 megameters per second, which is 1.2 times 10 to the 6 meters per second. The field is 640 newtons per coulomb. And the proton has a charge of 1.6 times 10 to the minus 19 coulombs and a mass of 1.67 times 10 to the 27 to 10 to the minus 27 coulombs. So these are our, let me prepare here in case I have to write some, let me make it blue so it'll look different than what I've already got written. Okay, so let's look at our knowns. We know VI is equal to 0 meters per second. V initial is 0 meters per second. V final is 1.2 megameters per second. E is equal to 640 newtons per coulomb. And Q, the charge, is equal to 1.6 times 10 to the minus 19 coulombs. Okay, and we know that the mass from the table 22.1, is 1.67 times 10 to the minus 27 kilograms. Now, we just learned from the last equation on the previous slide that the acceleration is equal to QE divided by m. That's equation 22.1 in your text. So we're just going to apply this equation. The acceleration is the Q, which is 1.6 times 10 to the minus 19 coulombs. I've already got the coulombs scratched out. I probably shouldn't do that. Whoops. Let's change it back to red. Okay. We'll go to blue. Okay, so we've got the acceleration is equal to 1.6 times 10 to the minus 19 coulombs times 640 newtons per coulomb, and divided by the mass of 1.67 times 10 to the minus 27 kilograms. And if you multiply that all of that out, you'll get 6.13 times 10 to the 10th meters per second. Well, how do we get meters per second from all this? Well, the coulombs cancel, and we have newtons per kilogram, and that's newtons is kilogram meters per second squared divided by kilograms. The kilograms cancel, so that's equal to meters per second squared, and that's what we want. Okay, let's go on. So that's A. A is find the acceleration of the proton. We get 6.13 times 10 to the 10th meters per second. That's a strong acceleration. The question B is over what time interval does the proton reach the speed? Well, let's think about the definition of acceleration. Acceleration is delta V over delta T. That's our acceleration. So delta V is equal to V final minus V initial divided by delta T. Well, let's solve for delta T, and delta T is equal to V final minus V initial over the acceleration. So if we make that substitution, we have delta T is equal to 1.2 times 10 to the 6 meters per second. That's our V final minus V initial is 0 meters per second divided by the acceleration, 6.13 times 10 to the 10th meters per second, which we just calculated. And it's going to give us 1.96 times 10 to the minus 5 seconds, which is 19.6 times 10 to the minus 6 seconds, which is 19.6 microcoulombs. And you can see that if we have meters per second over meters per second squared, we're going to end up with 1 over seconds, and that ends up being seconds. Now it's 10 to the minus, it's 19.6 times 10 to the minus 6 seconds, so that gives us microseconds. So that's how we get our units. Now let's look at C. C says, how far does it move in this time interval? Well, we're going to go all the way back to our equations of motion. How far it travels is equal to x initial plus v initial times t plus 1/2 acceleration times t squared. Dig way back in your memory from first semester physics, and that's the equation of motion to get the distance traveled. Well, x initial is 0, v initial is 0, so that simplifies the equation to just x equals 1/2 at squared. I have the initial conditions there. So let's look at the equation now. We have x is equal to 1/2 times the acceleration times time squared. So it's 1/2 times 6.13 times 10 to the 10th meters per second squared times the time squared, which is 19.6 microseconds squared. If you multiply all that out, you get 11.7 meters. It's easy to see that we have meters per second squared. The microseconds are going to be seconds squared, so that cancels, and all we're left with is meters. And so that's the answer there. Now let's look at the last part. What is the kinetic energy at the end of this interval? Well, kinetic energy is KE. Kinetic energy is equal to 1/2 mv squared. So we take the 1/2 times the mass, 1.67 times 10 to the minus 27 kilograms, times the final velocity, 1.2 times 10 to the 6 meters per second squared. And if you multiply that out, we get 1.2 times 10 to the minus 15 joules. We have kilogram times meters squared per second squared, and we break that up, kilogram meters per second squared times meters. This part of it is newtons, so we end up Newton meters, which is, as you know, joules. Okay, so that ends our discussion, and there's an example problem as to how to handle this this particle in a motion of a charged particle in a uniform electric field. All right.